Module 1, Lesson 5, Pure Substances and Mixtures. Why study matter? Well, by now, you probably figured out that matter is an important concept in all fields of science. Regardless of which field you're in, scientists are dealing with matter. For example, in chemistry, chemists study the structure, composition, properties, and changes of matter. In biology, biologists study the structure, function, growth, and evolution of living matter. In physics, physicists study the motion of matter through space and time and the effects of forces on matter. Sorting matter. Matter has two main divisions. The first one being pure substances. Pure substances are matter with a constant composition. All particles have the same properties. So, for example, water or helium. Versus the other division of mixture. Mixtures are matter with variable composition. So, those are made from two or more substances, such as sand and soil. Let's take a closer look at pure substances. Pure substances are divided into two groups, elements and compounds. So an element is a substance made up of atoms with the same atomic number. In other words, if you can find it on the periodic table, it is an element. For example, calcium, gold, silver, sodium, helium, fluorine. A compound is a substance made from two or more elements chemically combined. So this one's a little trickier, but still easy enough to understand. Compounds are made of two or more different elements that have chemically combined. So let's take a closer look at compounds. Now, compounds are a pure substance, but what makes them a pure substance? Well, first off, they have a chemical formula. For example, water. No matter where you go, pure water is always made of 2 hydrogen atoms and 1 oxygen. 2. Their properties are all their own. This means that they are very much different than the elements that combine to make them. Their properties change. So let's take a look at an example here. So we have hydrogen, which is a highly reactive element. It's a gas at room temperature. We use it for a fuel. It's flammable. It has a boiling point of negative 253 degrees Celsius. Okay, now we got oxygen. Again, a highly reactive gas at room temperature. Oxygen feeds fires. Humans and animals, we need it to breathe. And it has a boiling point of negative 183 degrees Celsius. Now, when you combine hydrogen and oxygen, you get water. Non-reactive, liquid at room temperature. Water puts out fires. We can't breathe in water, and it has a boiling point of 100 degrees Celsius. So if you look at what water is made of, you'll see how the properties really change. Okay, let's take a look at another example. Sodium, extremely reactive, shiny, soft metal. It's conductive electrically and thermally, and it has a boiling point of over 800 degrees Celsius. Chlorine, extremely reactive, poisonous. At room temperature, it's a gas, yellow and green gas. It's a non-metal. Chlorine has a distinctive bleach smell to it and a boiling point of negative 34 degrees Celsius. Now you combine that together, you get table salt, NaCl. This is an edible seasoning. We use it to preserve food. At room temperature, it's a solid crystal, no real distinctive smell, and a boiling point of approximately 1,400 degrees Celsius. Now, if you look at what makes table salt, sodium and chlorine, both extremely reactive, would kill us if we ate it, but combined completely changes, and we put salt on a lot of things. We eat it all the time. So let's take a look at a couple more examples. First one here we have is glucose, C6H12O6. Citric acid, it's made of 6 carbons, 8 hydrogens, and 7 oxygens. This is vitamin C. And then the last one we'll look at here is acetic acid. It's made with 2 carbons, 4 hydrogens, and 2 oxygens. This is what makes vinegar taste like vinegar, the acetic acid. Okay, I'd like to draw your attention to two things with these three examples. The first one is notice the elements in each of the compounds are the same, C's, H, and O's. They're just in different ratios. So here we've got, if we look here, both 6 carbons. This has 12 hydrogens, this only has 8. This has 6 oxygens, this has 1 more and 7, but 2 completely different compounds. Sugar, sweet, vitamin C, tart, right? And acetic acid, again, carbon, hydrogen, oxygen, but in different ratios makes a completely different compound. And number 2, you're looking at 3 different representations of a molecule. The first one here is a Lewis structure, and you'll learn more about those when you move into chemistry. Down here we have a ball and stick model. As you can see, you've got balls, and these lines here represent bonds. And the last model is a space-filling model. And you'll see that all the atoms are put close together, and there is no space in between. Okay, so now that we know the 2 types of pure substances, let's sort some out here. So we have 2 options, element, which is the same element by itself, or compounds, which is made of 2 or more different elements chemically combined. So let's give this a go. So potassium, where would you put that one? Element. Okay, hydrogen, just H. Again, an element. Table salt. We looked at that one in the last example. So you guessed it, that's a compound. It's made of 2 elements. Argon. AR, 1 symbol, 1 element. Element. Carbon dioxide. C, O, and 2. All chemically combined into a compound. Now oxygen's a little tricky. We have 2 oxygens. So is that an element or a compound? Now if you look down here at the definitions, oxygen is the same versus a compound, 2 or more different elements. So oxygen indeed is an element. Ammonia, NH3, you guessed it, 2 different elements chemically combined. Well done. Okay, a little more practice. This is a particle representation of either an element or a compound. So we have 5 different representations. Each of these circles represent an atom. So in this one here, we have all black, round particles. So that represents an element. In our next example, we have 4 white circles surrounding a black circle in the middle. So this represents a compound, different elements combined. The next one, again, 2 different types of circles or particles chemically combined. So that's a compound. This one here, we have 2 circles, 2 particles, yet they're the same. So that's like our O2, that's an element. And then this last one, you can see you've got 2 whites joining the black on the outsides there, and they're all the same. So that's a compound. So hopefully you were able to sort those with no problem. Good job. Okay, so classification of matter. So we have matter up here, and as discussed, we have pure substances versus mixture. So we've just talked about elements. So one type of atom, and you can see they're represented by movement. Particles are always moving. Compounds, again, you can see the movement of them, but you'll see they're represented by 2 or more different atoms chemically combined. Okay, so now we're going to go take a look at mixtures. So mixtures are just what they sound like. Different pure substances, either atoms or compounds, mixing together in variable compositions. The key here is nothing changes. So for example, you add some salt to water, it's just salty water. The more salt you put in, the higher the concentration of the salt. Milk to coffee, just get like a milky coffee. You put a diamond and a ring together, gold ring, you just get a diamond ring. Rocks to water, just rocks and water. So the key again is the substances have not changed. They're just mixed together. So if we go back to this chart here, you'll see there's two types of mixtures, homogeneous and heterogeneous. So let's go take a look at those. Homogeneous mixtures. So if we break down the word here and look at the beginning, homo, that means the same. So homogeneous mixtures will look the same throughout, and we call these solutions. So from our last page of examples, both salt water and milky coffee are examples of homogeneous solutions because they look the same throughout. You couldn't really tell what's in here, and you couldn't really tell what's in here. It looks the same. Another homogeneous solution is the air. It's a whole mixture of all kinds of different gases, but to us, it just looks the same. Heterogeneous mixtures. We break down the word. Hetero can be defined as different. So therefore, heterogeneous mixtures have different parts. From our 2 pages ago of examples, both the diamond ring and the rocks and water are heterogeneous because they don't look the same. There's different parts to them. Just like chicken soup, you've got all kinds of different parts in here. It's a heterogeneous mixture. Okay, a little more particle practice. So I've got 4 representations this time. If I look at this first box, I would see that there's 2 different atoms chemically combined into a compound. Looking at this next one, we've got 4, at least 4 particles, different, so again a compound. Now here I've got, again, molecules, but they look the same, So this would be a mixture, because I have 2 different types of 2 elements, and they're diatomic molecules. Now this last one here, I've got red balls here, and I've got this compound. So again, I've got a mixture of different things. I have a mixture of an element and a compound. Okay, last slide here. So I hope you found this information informative. Please continue your discovery and complete your notes by defining and providing an example of the following types of mixtures: colloid, emulsion, and suspension. Now at first glance, these type of mixtures may look like a homogeneous solution, but if you dig a bit deeper into their definition, you'll find that they're not. Just like this glass of milk. The milk may look homogeneous, but I bet if you got close up, you would see a different story. Okay, thanks for watching, and have fun with this lesson.